Hello everyone, welcome back for DMS lecture. Uh, just go through the previous slides. So previously we have a design, we have started build convert design. Previously we have assumed some data. Based on that we can find out the determine belt design. Then we have completed our motor power design. Motor design, we have selected suitable motor according to the output required. Okay, now next, design of pulley design with the shaft and bearing. Now calculating the effective load while transmission is very important to maintain the tension. So for that, the hidden drive system, we calculating the tensions by assuming that the driving pulley is a head driven pulley. Okay, so referring PhD page number 9.18, T1 is equal to P into e raised to mu alpha divided by e raised to mu alpha minus 1. So here mu is the coefficient of friction between belt and pulley. It could be in between 0.1 to 0.4. We're considering generalized 0.3. By considering a pulley material of cast iron without lining, and the working environment is a dusty environment, the angle of lap is considered alpha 200 degree, which is equal to 3.491 radian. So putting all the values, what we get, T1 is equal to 1063.9 kgf. Okay, so if you want, you can check on PhD also, PhD page number 9.18. Here the all formulas related to the tension is given in the slot. By considering various options, T1 you can calculate over here, T2 you can calculate over here, T3 you can calculate over here, and T4 here. So we are considering the hidden drive. So this one is a we have considered. So we have to always looking for this column only. Okay. Okay. The standard data is given over here. You can get that data from PhD also. Okay. Go to the next. If we after calculation of T1, now next go for calculating the value of T2. For T2, the equation given in PhD, we just look at over here. Okay, for head ended, it is T1, sorry, over here, T1 minus P. Okay, by considering this same equation, we can use in a design T2 is equal to T1 minus P. So we know the value of T1 and P. Putting all the values, what you get, T2 is equal to 373.309 kgf. Now next T3 is T2 plus WU. So again similarly we can putting the T2 and WU value. T3 is equal to 301.1014 kgf. T4 is equal to T3 as shown as per the PhD. Okay, here T2 T3 is equal to T2 plus W and T4 is equal to T3. Okay, as the head driving mechanism is considered. Okay, if you consider tail drive, the value get varied. Okay, so we all tensions we have calculated. Okay, now next one, to determine identify the number of plies on the layer. For that we have considered few considerations. The end of the belt is joined by these two different ways as follows. First one is a vulcanization and second one is a mechanical joint. In a vulcanization, the joint is done by hot or cold cemented using a special adhesive between pressurized plate. So in this way, the vulcanization has been done. And generally, we have seen in normal day-to-day life when our bicycle or simpler motorcycle get punctured, and the mechanic, you can say, the person who is expertization in making removing that puncture, that will be normally passes through such vulcanization process. So they are applying the adhesive and then putting a small piece of rubber over there, and they apply the pressure and continued temperature so that the process can be done, and they can properly mix with each other. So in a similar manner, that vulcanization process occurs, and in the same way you can connect both ends of the pulley. Second one is a mechanical joint. With the help of metallic strips, hinges, or rivets in the lap joint, we can join the both ends. Okay, but out of the both, the vulcanization is best and more reliable method, because in a mechanical joint it could be possibility that whenever to attach those hinges or staples, we are producing holes, or you can say automatically when apply the staple, the holes are get produced, and due to the continuous temperature or continuous tensile force, that holes get enlarged, and similarly the total efficiency or the lifespan of that built segment get reduced. Okay, so for this reason, the vulcanization is considered as the best and reliable method. Now, referring PhD page number 9.21, go to the PhD page number 9.21. What we can find out? Sorry, it's 2. Okay. So from here in this table number 4, you can find out the yeah. Okay. So based on the belt width, you can get a actual density of the conveyor material. Okay, from this table number 4. Then we have to find out the designation of belt fabricated. It is in a form of OZ. Okay. So how it could be decided? It could be decided based on the belt width, which is shown over here. Then the number of plies, that could be 28, 32. Okay. So based on this velocity ratio, that the variation, or you can see the different segments are generated. So here these are the 4 different ratios. So here the first segment, that is for over 0.4 to 0.85, second segment 0.85 to 1.5, and third segment, that is in between 1.25 to 1.75, and the fourth and last segment is over here, that is 1.75 to 2.75. Now select the appropriate diameter and find out the lap plus the density of material. Okay, so in this manner you can easily find out the um, belt designation. Okay, now another way, that is from table number 5. Okay, in the table number 5, what we get, actually we can easily find out the designation of the belt. Okay, here the designations are given, but we don't know which one is a suitable one. So for that, the table number 5 will help us. As we have selected the vulcanized joint and the working tension kg per width ply is given over here. Okay, so from this you can select a appropriate value and find out the belt designation. Okay, let's see in the go to the calculation. Okay, so the density of the material conveyed is 1.3 ton per meter cube, and the width of the belt is a 500 mm. So recommended fabrics are 28 OZ, 32 OZ, 36 OZ, 46 OZ, and 48 OZ. Now considering these are two considerations, that is 32 OZ and 36 OZ. Okay, as the density of material is 1.3, as the density of material is 1.3. Let's see in the table, as density of material is 1.3, so it lies in this segment. It lies in this segment. Now based on the material consideration, okay, it lies in between this one. Now you can go with the 32, 36, 42 and 48. Okay, so out of this you can choose depend. Okay, another, you have a width, you can go in this way. So the maximum number for 32 is 5 and minimum number of plies are 4. Similarly in 36 also there is the same. Okay, so let's see in the calculation part. Okay, so these are the maximum and minimum allowable plies, as I have also shown you in PhD. So let's initially calculate the number of plies, so that whatever the calculated number of plies which is lies in between or not, that we have to consider. It should be the lesser than the given one, so that we can choose a appropriate belt. Next one, referring PhD page number 9.18, I, number of plies is equal to T1 divided by B into F. Okay, where F is the working tension of the belt for 1 meter width, which we can calculate from PhD page number 9.21 table number 5. That is, as I already suggested you. Okay, so 32, for 32 the value of F is 0.62, and for 36 the value of F is equal to 0.71. Just look at the table number 5 here, the table number 5, working tension. Okay, so here the values are given, we are with respect to the 32 and 36. Okay, so 0.62 and 0.71 based on the vulcanization joint and gravity take-up condition. Okay, so putting all the values, what we get for 32 OZ, the number of plies are 4, and for 36 OZ the number of plies are equal to 3. Okay, so by consideration with respect to the manufacturing cost point of view, we are selecting 32 OZ with the number of plies are 4. As we've seen, the minimum number of plies are 4 for 32, maximum you can go with the 5. Okay, okay, now next you can look at this diagram. That is design of pulley hub. Okay, so here the pulley is mounted over the bar, and the spacer in between the pulley and bearing is provided, so that the misalignment or the whatever the shocks occurred due to rotation while rotating, that could be absorbed by the spacer bush. Okay, and the proper alignment could be maintained. Okay, so these are few standard width lengths has been described over here. So pulley width, which is denoted by WB, then in between these two uh, centers, that is described by WB. Okay, so similarly we have given a proper appropriate nomenclature to everyone. Now here the stress diagram has shown how the loads are applied, okay, with the distance. Okay, now these pulley we can generally design for maximum bending condition. Okay, so Bmax is equal to Fs by 2 into L. You can simply sing from here to here. Okay, so distance is given L2, L1 or L2. So outside length we are considering L2. So from reaction purpose, when we calculating the maximum bending stress, that is called as momentum, we have calculated by using Fs by 2, that is a force, into the distance L2. Okay, LH is equal to Wp divided by, that is an basic assumption. So the length of hub is equal to width of pulley divided by 5. Assuming thickness of the TS here, the thickness of spacer bush is equal to 10 mm, and the thickness of the bearing is considered as a 40 mm. Okay, so L1 is equal to Wp minus LH divided by 2 plus LH divided by 2. So again L2 is equal to LH by 2 plus TS plus thickness of bearing divided by 2. Now from the handbook of conveyor, just a minute. The diameter D is equal to KPL into KP into I. Okay, so the KPL is the coefficient depends upon the strength of the towns, okay, per ply. So here the number of plies we have considering, and the standard values which is we can mentioned over here. So based on the strength, ply strength divided by ply strength in Newton meter, which is shown over here, and the value of KPL is also given. So in our cases, it is 6.2. Strength is 6.2. So the value of KPL is equal to 1.45. Okay. So the coefficient of P is depend upon the pulley, which is given over here. 1 for single pulley, 1.1 for double pulley, 0.8 for terminal, and a reverse with a take-up system, and 0.9 if the belt tension is up to 60% of allowable value, and 0.5 if the belt tension is exceeded than 60% of allowable value. So considering Kp is equal to 1 as a single pulley driven system, I number of plies we have already, that is number 4. So the diameter of pulley D is equal to 145 into 1 into 4. Okay, so this formula and this everything is haven't given into the PhD. So I suggest everyone to properly see the procedure. Here we have to calculate the diameter of pulley. D is equal to KPL into KP into I. We know the value of I. Okay, KP value you can consider from this table. Okay, and KP value you can consider from over here. Okay, so 145 into 1 into 4, what you get, the diameter of pulley is 580 mm, and the standard available pulley diameter, which is recommended diameter, is 630, available with the PhD page number 7.54. Okay, so the additional width of the pulley, referring with the PhD page number 7.54, the diameter is more than 500, so it is a 50 mm. Okay, so belt width plus pulley width is equal to uh, pulley diameter plus 50, that is 550 mm. Now next, go to the design of shaft. Okay, so design of shaft for driving pulley. If width of pulley is equal to 550 and the width of B is equal to 500, then the LH is equal to WP by 5, which we have already mentioned or considered. So the LH is equal to 110 mm. L1 is equal to WP minus LH divided by 2, LH divided by 2, that is nothing but 440 mm. L2 is equal to LH by 2 plus TS plus T bar by 2. So the L2 is equal to 85 mm. So the force Fs is equal to T1 plus T2. That T1 is equal to 1063.89 and T2 is 373.3. So F is equal to 14 point or 1437.19, or you can say 14.37 kilonewton. As we have already seen in this figure, the loading conditions, what we get, the maximum bending is equal to Fs divided by 2 into L1. So writing the value of L1, that is 85, Fs is equal to 1432, okay, 14.37 kilonewton, okay, and so maximum bending stress is equal to 6.1 into 10 raised to 5 Newton mm. Now the velocity, we have to calculate the peripheral velocity. To calculate the power we need a speed. To calculate exact speed, we can calculate that exact speed uh, based on the velocity, as the actual velocity we have calculated and at initial stage. So the actual velocity is 1.3035 equal to pi dn by 60. So here the diameter we have considered is 0.630. Okay, so n, which is calculated, is 39.51.58 rpm. Now we have a value of n, we have a value of p. Now calculate the value of mt, torsional moment. Okay, so p is equal to 2 pi mt divided by 60. Putting all the values, mt is equal to 2658.22 Newton meter. Convert into the mm, that is 2.65 into 10 raised to 6 Newton mm. Now taking an equivalent twisting moment, Te is equal to square root of kt mb square plus kd into mt square. We are considering the gradual shock condition. Kt is equal to 1.75 and kd is equal to 1.25. So putting all the values, the twisted moment is equal to T is equal to 3.071 into 10 raised to 6 Newton mm. Now we are going to design a shaft. For that, the material of the shaft is considered as a C45. The values related to C45 as note down over here. Okay, calculated the working as well as design stresses. So T is equal to pi dn by d cube ts cube into the tau. So from that we calculated the diameter of the shaft, that is 63.88 mm. Okay, we have converted or modified to 70 mm by considering the dynamic load and the self weight of the pulley, so it could be withstand very well. So diameter of hub is the twice the diameter of the shaft, that is diameter of hub is equal to 140 mm. Now the thickness of wave of that pulley is considered as 20 mm and the TR is equal to 10 mm. Now next one, selecting the bearing for a pulley drive. Referring page number 4.5. The LH value or L90 value we are considering for 12 hours, 12,000 hours by considering the mechanical working intermediately. Machine is working intermediately, and those breakdown would have a serious sequence consequences. So here a belt conveyor should not be breakdown, that we know that. So based on this application we have considered that much life. So we have considered converting this L value of life into how hours into the revolution RPM. Okay, sorry, revolution, million revolution. So L90 is equal to LH90 into 60 into NP. What do we get? So L90 is equal to 23.45 into 10 raised to 6 million revolutions. 23.45 million revolutions. The effective load P effective is equal to CR into Fx plus Y into Fa into service factor. So Fr is equal to Fs by 2, 14371.9 divided by 2. So Fr is equal to 7185.94 Newton. Neglecting the axial momentum, CR is equal to 1.1 as the inner race is rotating, and the rotary machine without no impact, the service factor is 1.4. Considering X is equal to 1 and Y is equal to 0 because we are neglecting the axial momentum. So considering pure radial condition, so effective load is equal to, putting all the values, what we get, the effective load is equal to 11.0663 kilonewton. Now let's see calculating the value of C. C is equal to L90 divided by L10 raised to Kp into P effective. So Kp based on the roller bearing, if you're considering the roller bearing, the value of K is equal to 10 by 3. Okay, so putting all the values, what you get, C is equal to 30,215.48 Newton or 3,221.54 kgf. Referring PSG, considering the cylindrical roller bearing, as the continuous load is occurring only in a radial direction rather than considering the ball bearing, we are go with the roller bearing. So diameter of shaft is 70 mm. Value of C which is required is 3021.54. Okay, so SKF bearing we have selected SKF and U2214, having the value of C is equal to 8800 kgf and C0 is equal to 8000 kgf, which is more stiffen, or you can say more sustainable. Okay, now next the design of shaft for tail pulley. The force on the take-up device is roughly considered as twice the tractive tension of the force. So F force on the take-up pulley is equal to twice of T3, that is a tractive force, or you can say tractive tension. So F take-up is equal to 602.8 kgf. Now the bending moment is the same as that of the driven pulley. So diameter of shaft is equal to 70 mm. Okay. Now next the design of troughing idler. Okay. So design of the troughing idler we will discuss in next lecture. In the next lecture we will cover up the design of troughing idler, then the bearing for troughing idler, then shaft design, then design for a return idler. Okay, and bearing for same. Okay, we will check also basic reduction ratio for gearbox if you want to design for same. Okay, so in the next lecture we will discuss the further